This lab uses Newton's second law to analyze the motion of a falling ball of paper. The object was analyzed in Tracker, and two models were made in Vital. One model accounted only for the force of gravity, while the other accounted for both gravity and drag force. The model with drag force included was far more accurate to what happened than the model without drag force, though was also not entirely accurate. Newton's second law, in its simplest form, states that the net force on an object equals the mass of the object times acceleration. This can be derived to the equation final velocity equals initial velocity plus the net force on the object divided by its mass times the change in time. This equation can be further derived to the equation final position equals initial position plus the average velocity times the change in time. A paper ball was dropped and analyzed in Tracker. Using the height of the bricks, the footage was calibrated, and the origin was slightly above the ball when it was at rest. The position at every frame was taken. From this, we determined the initial position to be negative 0.039 meters, and since the object begins at rest, the initial velocity was 0. There are two major forces that are affecting our system: gravity, or the force of attraction between objects in the universe, and drag, or the resistance of the air against the motion of an object. The force of gravity between two objects can be calculated with the equation the magnitude of the force of gravity of 1 on 2 equals the universal gravitational constant times the mass of object 1 multiplied by the mass of object 2 divided by the distance between the objects squared, where g, the universal gravitational constant, is 6.6 times 10 to the negative 11. This equation treats objects as points and spheres, and on the Earth's surface, the radius of the Earth is used as the distance. Due to the difference in scale, the height from which we drop the ball is negligible. From this equation, we get the formula f of g for Earth on the object to be 9.8 meters per second squared times the mass of the object in kilograms. Using this as our only force, a model was constructed. The initial position, velocity, the mass of the system, as well as the equation for gravity was entered into the code and gave us this model. The data from the model and the data from Tracker were used to construct a graph. As shown here, the model grossly overestimates the acceleration and final position of the object. This leads to the conclusion that gravity is not the only force affecting the system. The other force that is assumed to affect the system is drag. Drag force is the force that opposes the motion of an object due to air resistance. It is always in the opposite direction of motion and is related to the velocity. It is given by the equation f of d equals negative some constant b times velocity. The constant b can be estimated and calculated in several ways. However, for this case, I used the square of the magnitude of the velocity as a base and then entered in different values of b until the final position of the model matched the final position from the Tracker analysis. From the Tracker, we found the final position to be negative 1.2 meters. The value for b in this case was found to be 0.004698. With the code modified to account for drag, the forces of gravity and drag can be compared. This was done through their visualization as arrows, as seen here. Since the new model used the final position to calculate the value of b, it matches at both the beginning position and in the ending position. Despite their matching in the beginning and in the end, there is still discrepancy in the interim. There are several explanations for the mismatch along the path of data. 1. We didn't use the true form of Newton's second law to calculate the new positions. Instead of finding the average velocity, we assumed that the final velocity was close enough to the average to make no difference. However, that difference could have been great enough to create the differences that we see on the graph. 2. The ball is seen moving in the positive x direction in the footage, meaning that there is a force along the x-axis that was not compensated for in the model. This means that the air was not just pushing up, but to the right as well. It could have easily caused this change. Despite the discrepancies between the drag model and the Tracker data, it is clear that the drag model is a far better estimate of the motion than the gravity-only model. It follows the curve better and does not overestimate the end position. In the lab, we simply dropped the paper ball, so the initial velocity was 0. However, what if the object was thrown? Would the terminal velocity change? Terminal velocity is the velocity reached when drag equals gravity, so the net force becomes 0. This means that constant velocity is reached and the object cannot increase in speed anymore. The terminal velocity is unaffected whether the object is dropped or thrown. The only thing affected is how soon the object reaches terminal velocity. The graph of two models, one thrown and one dropped, shows that the slope of both match after a time, leading to the assumption of matching terminal velocity. In conclusion, a model of a falling object is only slightly accurate so long as both the forces from drag and gravity are taken into account, and the terminal velocity is unchanged if an object is thrown or if it is dropped.